Okay, welcome back. So today I want to talk about the comparison theorem, which I've kind of highlighted here, which basically says if we've got a convergent integral and our integral is kind of smaller than that, then our smaller integral has to be convergent. And you can check worksheet 8. We'll have kind of fill in the blank version of this, and the full version of this theorem is in section 5.10 in Stewart's book. But let's just kind of see this in action, right? So imagine we wanted to calculate this integral down here, where we have the integral of e to the minus x squared from 1 to infinity. Now this is really hard, basically impossible, to find an antiderivative of this function using methods that we know. But what we can do is we can kind of notice that, well, e to the minus x squared is, well, that's really the same as 1 over e to the x squared. And if I think about this versus maybe 1 over something a little bit simpler, what if I just erase that exponent? And so I have 1 over e to the x squared versus e to the x. And my intuition tells me that this thing, this e to the x squared, this denominator should be much bigger than the denominator in e to the x. And so this leads me to believe that this inequality should be true. Okay? That 1 over e to the x squared is smaller than 1 over e to the x. And maybe I should do a check on that. So let's just check. So I check that by cross multiplying. So let's see, I want e to the x to be smaller than e to the x squared. And that'll be true if the exponent x is smaller than the exponent x squared. And that will be true if x is greater than, let me write it this way, if x is greater than 1. Okay. And we look back at our integral and we say, oh, our integral is going from 1 to infinity. And so, since our integral is going from 1 to infinity, that must mean that x is in this range. Okay. So we have this inequality. We know it's true. And so now we need to ask, does the integral from 1 to infinity of 1 over e to the x converge? And if it does, then we will be done by the comparison test, right? The comparison theorem, which will tell us that our integral is going to be of a smaller area or a smaller function, depending on how you want to think about it. And so that must mean that our integral must converge. Okay? And so now we've boiled it down to hopefully an easier integral. Okay? So this integral is, we're going to be able to evaluate that by doing the integral. Let's rewrite it as e to the minus x dx. Can write that as a limit as t goes to infinity of the integral from 1 to t e to the minus x dx. Let's see, limit as t goes to infinity. The antiderivative is going to be minus e to the minus x from t down to 1. There's a great chance to pause the video and check your final answer at the end. So I get minus e to the minus t plus e to the minus 1. And now when I evaluate that limit, as t goes to infinity, this term is going to go to 0. because I'm going to be doing e to the minus infinity, that's going to be a really small number. And this is a constant. This goes to e to the minus 1. So I'm going to get a final answer of e to the minus 1. So our integral from 1 to infinity of 1 over e to the x dx converges. Therefore, by the comparison theorem, our integral from 1 to infinity of e to the minus x squared dx converges. So that's a good example of how the comparison test can kind of show up in practice. On the next video, I'm going to do probably not all the steps on this, but we'll just talk about how to find a good comparison. And that would be kind of the next step in this process. So thanks for watching, and I'll see you soon.